Quantum computing is a highly advanced novel method for computation. Before you get scared and think it's too complicated for you to understand, don't worry, you don't need an engineer's understanding for this video. Right now, we are only going to cover how quantum computing applies to our project. Here it goes. Quantum computers leverage specific quantum mechanical phenomena to do computation, namely superposition, entanglement, and interference. Our project deals mostly with superposition. Superposition is weird. It basically describes that two potential outcomes of an event that can't both happen at the same time. Both coexist before the event as probability in the form of an unstable probability wave. This wave wants to make up its mind but needs help to collapse itself out of waveform. That's where we can help the system decide what it's gonna do by measuring it. The outcome we measure is the outcome the wave collapsed to, and which outcome it collapsed to is purely random, or as random as we decide to specify. The inner mind of regular computers boils down into zeros and ones or bits. Every calculation is done with zeros or ones or bits. Quantum computers are fundamentally different. They do computation with qubits, which can be 0, 1, or any self-contained combination of part 1 and part 0. Don't think too hard about that if it confuses you. Just know that instead of two possible values, qubits have an infinite number of potential states. And just like we'd expect, its quantum states collapse out of waveform into a 0 or 1. The special part is we can do computation with qubits still in waveform before they collapse. For the sake of the project, our group interprets quantum randomness as the quantum computer making a decision. Art as a practice boils down to an artist making decisions. This begs the question, is a quantum computer an artist? We argue yes and proved it with our quantum music project. Quantum computers are exponentially more powerful than classical computers because qubits can be 0 and 1 at the same time. The technology is still in its infancy though, so if we set a qubit to 0 and measure it after an operation, we might still measure it as 1. We call this noise. Our project starts with a custom quantum circuit, similar to a computer program in classical computing. The circuit is made of 4 qubits, meaning it can output one of 16 potential numbers with a randomness specified by the circuit. Our circuit was designed to output only one of 12 numbers, but because of the noise, we knew we would also see the other 4 numbers in our results. Using Python, we interpreted each number as a computer playing a musical note on a pentatonic scale. We then ran our circuit a couple thousand times, and boom! We got a one-time unique song in MIDI format with a couple thousand notes that the quantum computer composed in 30.2 seconds. At 120 beats per minute, that makes the song a couple hours in length. The MIDI data in digital audio workstation like Ableton or Logic can be heard as sound. We use Logic Pro X. Using all the data specified in the circuit, like the noise and the numbers that specified each qubit's superposition, we texturized the music with effects like compression, distortion, reverb, delay, and modulation to make it sound more dynamic, less robotic. To add depth, we interpreted every 8th musical note as the bass notes for the next bar, and added rhythm with some percussion played by a human. The main melody is a summing instrument made of a flute, a piano, a trumpet, and a guitar, each representing a qubit with its texture specified by the circuit. Finally, we had heard the quantum song, but wanted the album cover to accompany it. So, with the same data as the song, we treated musical notes for colors and made a visual. We colored the noise data in different color scales as well to make it stand out like we did distortion in the song. In theory, you could follow the song as you listen by looking at the cover. The music in the background of the video is our quantum song.